Good morning. In the last class we were dealing with liquid propellants, and we continue on it, but before continuing on it I would like to clarify that the classification of liquid propellants was distinctly different from the way we classified solid propellants. While we classified solid propellants into something like a double base, a composite, a mixture of composite, that is composite modified double base and nitramine propellants. In the case of liquid propellants we had a somewhat different classification. We told ourselves the propellant could be a low energy propellant, or else it could be something like a medium energy propellant, or it could be something like a high energy propellant. In today's class we continue with this classification, and also we will try to see whether any other classification is also possible, so that we cover the entire spectrum of the different liquid fuels and liquid oxidizers which comprise the liquid propellants. For high energy we told ourselves, well, hydrogen and oxygen which have the low molecular mass are typically used, not because it has a high energy, but not only high energy but also a low value of the molecular mass of the products. We also said maybe hydrogen with respect to fluorine will also be a high energy, but fluorine being very reactive, this is not really used as a propellant. This was the high energy, and we said high energy are those which have specific impulse greater than 4000 Newton second by kilogram, right. We then came down to the low energy propellants. We said these are propellants which have specific impulses less than maybe 3000 Newton second by kilogram, and for this we considered, maybe we started with LOX, with we said alcohol, which was used in the V2 rocket in 1945. It was developed by the Germans. It was the first flying rocket, and therefore I always take this as an example. But alcohol contains oxygen also in addition to hydrocarbon, therefore it is not that energetic. From here we went to LOX, kerosene. When we looked at kerosene we found, well, kerosene was something like an aliphatic compound. We said something like C12 H26, and it has, since it comes from a petroleum base, it also contains some other constituent. It is not a pure chemical as it is, and therefore while using it we need to be a little careful, and we do not use raw kerosene acid, because raw kerosene we said has a flash point around 38 degrees centigrade or so, and we wanted to increase it to something like 45 degrees centigrade, for which we added additives to this and called the resultant thing as a rocket propellant. Kerosene is basically referred to as a rocket propellant, but we put some additives into kerosene such that the flash point, you all would have read about flash point and fire point. Flash point is there where you have some vapor coming but the flame cannot persist, whereas fire point is one wherein we have so much of copious vapor such that even when you remove the ignition source the fire continues. Therefore the flash point of kerosene is around 38, we increase it slightly to 45 or higher, and also when you heat kerosene in the absence of oxygen it should not form solid like coke, and coking temperature, by adding additives we make sure it is greater than around 550 Kelvin, such that when you inject something it should not block something if it is heated and all that. Therefore basically when we say LOX kerosene we talk in terms of LOX with the rocket propellant. This combination is also referred to as rocket propellant, even though kerosene we call as rocket propellant or LOX kerosene as rocket propellant. It is not correct to say a combination because I could use it with different mixture ratios. Well, this is one which we studied. Let us see what are the other combinations of oxidizer and fuel which could be the low energy, and that is what I start with today. Well, what did we do? We considered LOX as an oxidizer. Why should LOX alone be an oxidizer? Any substance which has excess oxygen could be an oxidizer. Maybe we could have HNO3 nitric acid, And if you see HNO3, you have one H and nitrogen anyway is inert, you have 3 of oxygen, what you need is half H2O, that means I still have 2 of excess oxygen, therefore nitric acid can be used as an oxidizer, and it is used as an oxidizer. I could also consider the other substance, maybe N2O4, and if you see HNO3, we saw while we looking at the heat of formation, it had something like minus 170 kilojoules per mole was the heat of formation, whereas N2O4 had a slightly positive heat of formation, and we told ourselves for propellant, if the fuel and oxidizer have positive or small negative values would be better, therefore N2O4 tends to be a better oxidizer compared to nitric acid. The thing is also apparent to you, you are losing some oxygen to the hydrogen, whereas in the case of N2O4 all the oxygen is available to you, therefore N2O4 is also used as an oxidizer. Let us go a little deeper, because HNO3 was used extensively and is still used by the defense in some ways. You know, when you say HNO3, well, it can be used, but if you can add something like maybe 15% of NO2 to it, you know, you add more NO2 to it, that means you add more oxygen to it, it becomes more energetic, and therefore HNO3 is sort of energized by addition of something like 15% NO2, and what happens, you know, you have fumes of NO2 coming the moment you open the lid of the HNO3 tank, and this is known as red fuming nitric acid, or rather RFNA. Other words, you have nitric acid, you have 15% NO2 to it, and the moment you add this and you sort of want to charge this, or you open the can or you open the tank containing NO3, you have these fumes of NO2 coming, and they are orangish or reddish in color. We will see some photographs of some test firings, you will see some orangish fumes coming, and that is because of the excess NO2, and this nitric acid, when 15% NO2 is added, is known as red fuming nitric acid. If you add a smaller content, like let us say 0.5% NO2, it still fumes but not in red color, it is known as white fuming nitric acid. Both acids are used in practice as oxidizers. But then this acid is very corrosive, nitric acid, both RFNA, WFNA, red fuming nitric acid and white fuming nitric acid are extremely corrosive, and even any vessel you keep, it tends to corrode the vessel. Therefore, what we do is you add something like 0.5% of hydrofluoric acid to, let us say, RFNA, and this inhibits the corrosive nature of the oxidizer, and this is known as inhibited red fuming nitric acid, that means IRFNA. Therefore, you have nitric acid as red fuming nitric acid, white fuming nitric acid, and an additive hydrofluoric acid HF added to it, such that it is not that corrosive, and this is what is known as IRFNA. Therefore, while considering nitric acid, let us keep in mind RFNA, red fuming nitric acid, WFNA, white fuming nitric acid, and maybe modified or inhibited red fuming nitric acid. You could also have inhibited white fuming nitric acid. These are the different forms in which it is used, but as I said, it was used extensively by defense and in other establishments, but now the preferred fuel is N2O4, because this is more energetic considering the slightly positive heat of formation of N2O4. Well, these are about the only oxidizers which are used. People talk in terms of H2O2 being an oxidizer, because here also I find there is still excess oxygen over hydrogen. H2O, I am still left with one O over here, but it is a very mild oxidizer and it has a heat of formation which is again terribly negative, something like 180 kilojoule per mole, and therefore it is not an effective oxidizer as it is. In fact, H2O2 can directly also dissociate into H2O plus half O2, and this itself is exothermic, and this is used more as a monopropellant as a single inbuilt explosive consisting of oxygen and fuel rather than as an oxidizer. Therefore, the other two oxidizers which we can think in terms of maybe propellants are HNO3 and N2O4. Now, let us put the fuels down. These oxidizers will not be as strong as liquid oxygen for the simple reason you are having some little bit of nullifying effect of hydrogen, you are having an inert over here. Therefore, these are even whenever I use HNO3 with let us say kerosene or N2O4 with kerosene, well the performance is going to be even poorer than LOX kerosene, and therefore, combination of these oxidizers with the fuels what we considered like kerosene will still be low energy propellants. Let us take a look at fuels other than kerosene. We can talk in terms of what we talked earlier, hydrazine, N2H4, we called it as hydrazine. It is a very popular fuel. You know, this also had a slightly positive heat of formation, and therefore it's a good fuel as it is. You have lot of hydrogen, and therefore you could have molecular mass of the products could still be light and it could be usable. I can take one of the H over here, substitute it by a methyl radical. In other words, to hydrazine I write this as N2H4. I take one of the H out, I have H3 left, I substitute it with CH3. In other words, I substitute one methyl radical into the hydrazine and I get what is known as monomethyl hydrazine. While talking of different chemicals, you will recall I said hydrazine is an explosive in the sense it can directly dissociate, whereas monomethyl is also about the same, it has about the same heat of formation around plus 50 kilojoule per mole, but this has a higher specific heat and is not as reactive as hydrazine per se, and therefore the preference is to use monomethyl hydrazine rather than raw hydrazine, but hydrazine is also used. Being more reactive, we will see to it when we come to the chapter on combustion instability. Hydrazine tends to be a little unstable compared to monomethyl hydrazine. Well, I can keep on evolving, and the only other evolving feature around this is I can have, instead of having nitrogen, nitrogen, I have hydrazine, hydrogen, hydrogen. Instead of taking one hydrogen and substituting it by a methyl radical, on one side unsymmetrically I put one methyl radical here, one methyl radical here, and this is known as unsymmetrically. That means the molecule is no longer symmetric. I have something like unsymmetric dimethyl 2-methyl hydrazine, which is known as UDMH. It is not as strong as this because now you are adding little more molecules to it, but it is a very powerful fuel. Most of the boosters what we are using in our country, we make use of unsymmetrical dimethyl hydrazine. Therefore, the fuels which we have considered so far are UDMH, this is known as monomethyl hydrazine MMH, and hydrazine. These are the three fuels which we use, and these three fuels can be used with RFNA or with white fuming nitric acid, which is quite rare, or N2O4. That means I take these oxidizers, use it with hydrazine or monomethyl hydrazine or UDMH. See, monomethyl hydrazine has a high specific heat, little more expensive compared to UDMH. Therefore, wherever smaller quantities of fuel are required, we use monomethyl hydrazine, like in upper stages where I do not want to use so much of fuel. Hydrazine is also used especially in spacecrafts, but as I told you it is a little more reactive, whereas UDMH is more widely used for wherever large propellant requirements are there. All these three propellants, all these three fuels or something like can cause cancer, and there is a trend in today's world to get back in and substitute it by kerosene or something, because we say it is carcinogenic. But being rocketry and using small quantities over a period of launches, we take adequate precaution and still continue to use these fuels. Therefore, now I put the low energy fuels again. I said in addition to LOX kerosene, I could have N2O4 with monomethyl hydrazine or with unsymmetrical dimethyl hydrazine, either or, MMH with N2O4 or UDMH with N2O4. There is also one last fuel which we call as a mixture of 50% UDMH plus 50% hydrazine This is known as AZ50. That means 50% of this and 50% of this known as AZ50, which is also used with N2O4. This was used in some of the rockets developed in US, and therefore this is known as Aerozine 50. Therefore, now I tell myself, well, the low energy propellants could be LOX kerosene, well this is outdated, or else when kerosene is substituted or LOX is substituted by HNO3 and let us say HNO3 in the form of red fuming nitric acid, which is more energetic, and fuels could be MMH, N2O4 or hydrazine. This is one class of this, or UDMH. This is the low energy propellants. You know, I think it is necessary to go back in history, because when we go back and see some of the missiles, we still see some other fuels being used, two other fuels being used, especially at DRDL when they were making these missiles earlier, and they still continue with it. One is known as aniline. See, while all the fuels what we considered were somewhat based on aliphatic, like kerosene, we say C all in the straight chain. Aniline is derived from an aromatic compound, aromatic chain, which is actually the benzene chain. And what is benzene chain? You have C, 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 C and alternate double bonds, 1, 2, 3, and you have H over here. One, 2, 3, 4, 5 and 6. What you do in aniline is you take the benzene chain, or you take benzene, substitute one of the hydrogen by amine radical NH2, and this becomes what we call as aniline. Let us keep this in mind, because I will come back to something, you know, this NH2 over here, or we say NH2 in hydrazine, or you say NH2 in MMH and UDMH is what is an amine radical, and this amine radical is so unstable, or it is so reactive, that the moment it comes in contact with, let us say, HNO3, or it comes in contact with N2O4, it by itself ignites and reacts, and such of the propellants which contain this amine radical readily react with HNO3 and N2O4, and such propellant combinations of HNO3, N2O4 with anything like aniline maybe, or with hydrazine, or UDMH or MMH will not therefore require an ignition source. All what I do is I put a fuel, one of these fuels, I put one of these oxidizers into the chamber, immediately by itself it will ignite, and these are known as hypergolic propellants. That why is it hypergolic? The amine radical in these fuels readily goes and reacts with the acid or the N2O4 to form hot combustion products. Therefore, the design of the rocket becomes simple. I just have a chamber, all what I need is I have to push this fuel having the amine radical in it, push the oxidizer, by itself it burns and it rejects gas. I do not even need to ignite it, I do not need an auxiliary igniter. Whereas if I talk of even hydrogen, liquid oxygen and kerosene, I need to ignite it because I have to overcome the energy barrier before an ignition reaction, chemical reaction can take place. Therefore, these are all hypergolic propellants, and we call those which require an ignition source for initiating reactions or combustion as non-hypergolic. These are liquid oxygen, liquid hydrogen, non-hypergolic, maybe liquid oxygen, kerosene. The only exception is liquid fluorine and liquid hydrogen. Liquid fluorine is so reactive that it will react with anything, with the container it will react, therefore it is also, it comes in the category of hypergolic, but mind you, it does not contain an amine, it comes from the reactivity of fluorine itself. This aniline was extensively used in the 70s and 80s, but as a slight improvement over aniline, one very last fuel which I will talk of is known as xylidine. And in xylidine what you do is you have the same aromatic structure, you have alternate double bonds, you had NH2 here, this was aniline, and you had the rebalance was all hydrogen over here. You take two more of the hydrogen atoms, maybe I remove one of the hydrogen atom, substitute it by a methyl radical, I remove this, substitute it by a methyl radical, and this is what is known as xylidine. Again it consists an amine radical and therefore it is hypergolic. These two, namely aniline and xylidine, are used as liquid fuels for many of the missiles. They are low performing, very low energetic, and therefore if I were to at this point in time just summarize what are the low energy propellants, maybe in terms of the energetics I can say, well, IRFNA with maybe xylidine or aniline, then I say maybe N2O4 is little better, maybe with the same combination, maybe N2O4 will be still better with hydrazine, maybe with UDMH, maybe with MMH, unsymmetrical dimethylhydrazine, monomethylhydrazine, and then the last one which we say is maybe LOX with kerosene. These are the low energy propellants, ISP increasing towards this, but the ceiling is less than 3000 Newton second by kilogram. Therefore, these are the low energy propellants, and many of these low energy propellants, especially those using the nitric acid and N2O4, are hypergolic, which means they are much easier to use, and that is why we see these fuels being repeatedly used in spite of being carcinogenic. It is much easier to use, and also we find the system becomes very simple. You do not need an auxiliary igniter, you can whenever you want you just fire it. Supposing I have a spacecraft, let us say, in the spacecraft you just carry a tank, let us say you carry an N2O4 tank, and that is what is done in our INSAT spacecrafts. You have a tank which carries N2O4, another tank you carry let us say monomethylhydrazine, mind you both are low energy fuels, and whenever you want to have some correction, maybe at the you have a series of rockets which are fed from these lines, maybe let us say I have one small rocket over here, maybe I take the fuel here, then again I have the another rocket over here, I take more of this, and so on. I keep on continuing, maybe I have something like 12 rockets, and whenever I want to fire it, I just open the line with a valve, I admit a small quantity and it fires and it gives me an impulse and I can use it very simply. I do not need any other ignition device to be able to fire this, and that is the advantage of many of the low energy propellants. And of course, kerosene is an improvement over this, and kerosene is readily available, it is a very cheap fuel again, and that is why the majority of the boosters or the vehicles which require large quantities of fuel make use of liquid oxygen and kerosene. We are still to start with this activity in our country. The only problem is this becomes a semi cryogenic fuel. At this point in time, I will slightly divert myself and come back to the medium energy propellants a little later. Now that we covered hypergolic, non-hypergolic, we told some are simple. The classification of propellants can also be done being under how you can store the propellant. Why do we say storing is so important? Suppose we have a missile to take off. See, missile must be ready at any point in time. That means the tank must be always be having the fuel. Therefore, we say a propellant could be stored on earth, we say earth storable, or if I want to fly a spacecraft and the spacecraft goes around for 20 years or 25 years, the propellant must be there in the spacecraft for that time. That means it must be storable in space, that means space storable. Immediately when I say earth storable and space storable, I say by earth storable something which can be stored on the ground and immediately I can fire. I say, well, if I have to have LOX kerosene, I cannot just keep it on ground all the time, because LOX has to be kept under refrigerated conditions or insulated conditions. Therefore, this is not even earth storable, leave alone space storable. Similarly, LOX and liquid hydrogen are cryogenic fuels, semi cryogenic and cryogenic fuels. These are not earth storable, and only most of the low energy propellants What were the low energy propellants? We have red fuming nitric acid or N2O4 as oxidizer with a series of maybe hydrazine, UDMH, MMH were all the low energy propellants. These are all earth storable propellants. Whereas if I say space storable, it becomes even worse for me. In space I can get still lower temperatures, and therefore not all of these things may not be used. For instance, let us take an example. N2O4 is a very good oxidizer. Let us consider the freezing point of N2O4. The freezing point of N2O4 is around -9 degrees centigrade, and whenever we have a spacecraft, when it is not looking at the sun, the temperature comes down. Therefore, I need heaters to keep this warm. But if I were to add something like 3% of nitric acid oxide, that is NO, that means 3% nitric oxide to N2O4, I can increase the freezing point or make the freezing point, instead of being -9 degrees centigrade, to something like -15 degrees centigrade. Therefore, if I have to make the oxidizer perform in space, one of the things to be done is maybe I should add some additives like nitric oxide. If I add 3%, I have a little better, and these are known as mixed oxides of nitrogen, and since I add 3%, this is known as MON3. Therefore, all what we do is in the earth storable, when I have N2O4 as an oxidizer, if the same N2O4 has to be used in space for a prolonged period, then I have to decrease its freezing point. I do that by adding NO to it. If I add 3%, it is known as MON3. If I add something like 25% of NO, that means 25% of NO I add, I can decrease the freezing point to something like -55 degrees centigrade, which is even better. Therefore, in space I can still use maybe the other part of it fuel as MMH, but I substitute N2O4 by this, and this is the subtle difference between earth storable and space storable propellants. Cryogenic and semi cryogenic propellants are those which are neither earth storable or space storable. It can be used in launch vehicles. Before a rocket, maybe a day before that, I charge the propellants and immediately it takes off. It cannot be used for missiles, it cannot be used for satellites, it cannot be used for some other purposes like which we want to readily store and use. I think these are the different classifications, and therefore, what is it we have seen so far? We told ourselves, well, propellants are classified into low energy, high energy, and we have examined these things. In between the two, we could also have a medium energy propellant, which could be in the range of something like 3000 Newton second by kilogram specific impulse to 4000 Newton second by kilogram. Propellants which give specific impulse, and what specific impulse? Sea level specific impulse, because we found that vacuum specific impulse is much higher, and what we evaluate is on the ground. Therefore, whenever sea level specific impulse is less than 3000, I say it is low energy. When it is greater than 4000, I say high energy. Medium energy is this, but there are hardly any good medium energy propellants. The only things which we can think of is maybe instead of having LOX kerosene, if I use instead of LOX, if I use liquid fluorine, well, it gives a specific impulse greater than 3000, something like 3200, it could be a good candidate, but liquid fluorine cannot be used. The other is, we also told ourselves whenever I have something like RFNA N2O4, these are inferior to LOX because they contain some other elements over here. Therefore, if I can use something like LOX with one of these fuels, let us say UDMH, or let us say combination of UDMH and hydrazine, Aerozine 50, or let us say with MMH, these give higher performance exceeding 3000, and these are the medium energy propellants. But the only one which has been used so far in practice is the combination LOX and UDMH, and this has been used by Russians alone. Okay. Therefore, all what we have done with liquid propellants is, see, we talked in so many chemicals. Ultimately, when it came to usage, we just have things which can be counted on our fingertips. And what are they? Let us now put it down together such that we never forget it. We tell ourselves, well, high energy propellants are neither storable on earth or in space. We call it as, it could be LOX, liquid oxygen, and liquid hydrogen. The low energy propellants are things which are storable. Many of them are storable in space with little modifications like MON3 instead of N2O4 or MON25 instead of N2O4, and these are essentially, we said, hypergolic whenever you have the fuel which contains the amine radical in it. The low energy also had liquid oxygen and kerosene, which is not earth storable, neither is it space storable. You have the medium energy propellant, which is again semi cryogenic, liquid oxygen and UDMH. This is the only propellant which has been used in a rocket so far. Well, these are the classifications according to energy. We could classify it into hypergolic or non-hypergolic. Hypergolic are ones in which the oxidizer and the fuel, when they come in contact, it automatically burns, and that we will consider when we deal with liquid propellant rockets. Non-hypergolics which need an igniter to get the combustion started in the rocket. The last classification we also saw was earth storable liquid propellants, and we say space storable. The semi cryogenic and cryogenic are neither earth storable nor space storable. I think this is all about the different liquid propellants what we consider. Let us now quickly go through the last part of propellants, we have considered solid propellants, we have considered liquid propellants. Let us take a look at what are the things like hybrid propellants before we come and solve one or two small problems. What do you mean by hybrid propellants? Hybrid propellants are those propellants which are in a mixed phase. Maybe the oxidizer could be a solid, fuel could be a solid, whereas the other one could be a gas or a liquid. The usual practice is the fuel of hybrid propellants is in a solid form, something like HTPB, which we considered. What was HTPB? We told ourselves, well, it is polybutadiene, you have C, C, C and C, 2 double bonds. What was it? And you had something like 6 over here, 2 and 2 over here. This was what was a polybutadiene, and it was a chain as it is, maybe M over here. Maybe you use hydroxy terminated polybutadiene, that means I have one OH here, I have one OH here. This could be a fuel for this. What is the advantage we had with hydroxy terminated polybutadiene? Instead of having something like PBAN, which consisted of acrylic acid acrylonitrile, that means you had heavier substances, here you have lighter substances and therefore it is stronger. Therefore, a typical fuel, solid fuel is something like HTPB, and what is done is maybe you form a solid something like this, maybe with a hole in it, and then put it in a motor case, maybe attach it to a nozzle, and this becomes your solid fuel for the hybrid. Now I need an oxidizer. The oxidizer you inject oxidizer into it, namely the oxidizer could be anything what we have considered. And what are the oxidizers which we have been talking of so far? We said oxidizers could be liquid oxygen, could be N2O4, could be red fuming nitric acid, better still inhibited red fuming nitric acid. Well, use one of these things, and if I use some of these things and allow the liquid to come in contact with the solid, maybe it will begin to react, it reacts, and then I get the hot gases out. Well, these are the hybrid combinations, essentially are therefore HTPB as a solid fuel and one of these 3 oxidizers as a liquid oxidizer. So far people have not started, you never use something like a gaseous oxidizer because I need large volumes to store it, and the only hybrid which is used, and it is picking up again. There was a time in 80s when there was a lot of interest in hybrid rockets, but again nowadays these private companies in US are coming forward and they are trying to make some manned vehicles which will take tourists from ground to space and all that using hybrid rockets. There is some interest again on this. When we talk of liquid oxidizers, well, liquid oxygen is powerful enough. Can I make the value of the specific impulse of, let us say, liquid oxygen to be higher in some way than by modifying the property of the liquid oxygen itself? Let us tell ourselves, well, the specific impulse can be increased by either increasing the combustion temperature or reducing the molecular mass of the combustion products. Either you increase the temperature of the combustion products or you reduce the molecular mass of the combustion products. How do I do this is the question. Let us examine the following. Supposing I add liquid fluorine to liquid oxygen, then in that case maybe the fuel in the hybrid propellant, let us say hydrocarbon, originally when liquid oxygen is used gives me water. Now when I add some liquid fluorine to liquid oxygen, and mind you it is quite easy to add liquid fluorine to liquid oxygen because the boiling point of liquid fluorine and liquid oxygen are about the same. In addition to getting water, since I add fluorine I also get hydrogen fluoride. Therefore, the products of combustion now are with liquid fluorine added to liquid oxygen, I now get, in addition to H2O, I also get hydrogen fluoride. The molecular mass of water, namely H2O, is 18, 2 plus 16, 18 grams per mole. The molecular mass of hydrogen fluoride is 10 gram per mole. Therefore, you find that the act of adding liquid fluorine to liquid oxygen results in getting more of hydrogen fluoride as I increase the liquid fluorine in oxygen, and therefore, the net value of the molecular mass of products, which now you get hydrogen fluoride also, decreases, and therefore, since this decreases, molecular mass decreases, I get a higher value of specific impulse. Therefore, what is it you do? Maybe I add, let us say, 10% of liquid fluorine to a mixture of liquid oxygen and liquid fluorine. That means 10% of liquid fluorine in this particular mixture is known as flux, fluorine and liquid oxygen, 10%. If I add something like 70% of liquid fluorine to the liquid oxygen mixture, then I call it as flux 70. Therefore, by using flux instead of liquid oxygen LOX, I get much higher specific impulses, and therefore, these are considered to be higher energetic substance. The main aim therefore is, by using flux instead of liquid oxygen LOX, I get a higher value of specific impulse, and the higher value of specific impulse does not come from the energetics of the propellant alone, but by a reduction in the molecular mass of the products, which gives me the higher value of specific impulse. Let us keep this in mind, that is, I can improve the performance of propellants by reducing the molecular mass of the products. These are all the propellants, and to summarize the whole thing again, let us put the whole thing together. We talked propellants could either be solids, could be liquid, could be hybrid. We classified solids into 4 categories, and what were the 4 categories? We said it could be a double base or a single base, it could be a composite, in which case you have crystals of solid dispersed in a solution or dispersed in a material heterogeneously. It could be a combination of composite modified double base, that is double base and composite together, or nitramine. Liquids we just saw, we say space storable, earth storable, hypergolic, non-hypergolic. We said yes, low energy, medium energy and high energy, and of course we looked at hybrid propellants. Well, these are the only propellants which are in use today, and when we consider solid rockets, solid propellant rockets, liquid propellant rockets and hybrid propellant rockets, we will consider the details of how to make these rockets. What are the factors? There are a lot of factors. Will we look at the chemistry or will we look at the ballistics? Certain things we have to do, and that is what we will be doing from the next class onwards. I would like to give you one reference which makes extremely interesting reading, and that reference is a book called Ignition. It is there in our library. The name of the book is Ignition, an informal history of liquid rocket propellants. It is by John D. Clark. Quite an old book though, something like 1962 or so it came out, but gives a total coverage. It is not only these things, I am not only interested in the performance. See, the liquid propellant or any propellant, we must consider, like what we said, maybe storability, maybe the ignitability, maybe it must not be corrosive, it must be cheap, we have covered all that, and he brings it out beautifully. Like when they were handling these propellants, some acid would get into the flesh and eat into the system itself, therefore it is not usable. What are the defects, what are the explosives what could be used, and therefore something which makes an interesting reading. I think this is all about liquid propellants. Let us quickly do something like 1 or 2 small problems, such that we know how to solve problems in this particular area of liquid propellant. Let's do one or two small problems. The first one I choose is extremely simple but illustrative. Yes, supposing I say I'm using a propellant like let us say MMH and N2O4 as propellants, and I say I am going to use it for a mixture ratio of 1.5. That means the moment I choose a propellant I also choose the mixture ratio. Why? Because we told ourselves that if I plot ISP or C star, the ISP will be maximum in the fuel rich region and I will choose a fuel rich point. Therefore, this is known. Normally, even though I say now 1.5 might be here, I choose this because for simplicity in doing a problem, sometimes we will use a mixture ratio in which the volume quantities will be the same instead of taking, that means the Q of the hydrazine, the volume of N2O4 is same, such that I just need to develop one tank and the same tank I can use for both the purposes. Let's start with this problem. I say I am going to make a rocket using MMH and N2O4 at a mixture ratio of 1.5. I also am given one more data. I tell myself, well, the thrust what I require is 6.7 kilonewton is the thrust I need. Now I ask a question, what must be the mass flow rate of MMH into the chamber? What must be the mass flow rate of N2O4 in the chamber to give me a thrust of 6.7 kilonewton? Therefore, what I do, the problem is extremely simple. Well, the propellant combination is known. I know the formula for MMH, we said it is CH3 N2 H3. I know the formula for N2O4. I am given the particular mixture ratio mass of this, therefore I know what is the value of this. I can find out the temperature of the products, I can find out the composition of the products using dissociative equilibrium. We have covered it. Or if you want a simpler one, assume some products and do the problem. Assumed hydrogen to be much more reactive than carbon, and therefore hydrogen first tries to find out, searches for oxygen, consumes it, and only the balance of oxygen is left for carbon to react. The nitrogen in the substance is obtained in the products as N2. Therefore, the procedure is, first we use the hydrogen in the fuel which searches for the oxygen, consumes it. The balance oxygen is now available for carbon to react either fully to carbon dioxide or partially to carbon monoxide, or if even oxygen is not available, to carbon, and the nitrogen in the fuel or oxidizer is available in the products as N2. This procedure is quite useful in determining the combustion products for fuel rich mixtures, but it is possible, we must do the detailed problem. When I do it, I find that the temperature of the flame or temperature of the combustion products is 3028, the molecular mass of the products is equal to 20.39, this was based on dissociative equilibrium, and the value of gamma is equal to 1.235. Once I know this, I can get the value of C star. The C star is equal to, we told ourselves, is equal to under root R Tc by, if I in terms of universal, R naught by m, or rather I take it at the bottom, into 1 over capital gamma. We had capital gamma in terms of under root gamma, 2 over gamma plus 1 to the power gamma plus 1 divided by 2 gamma minus 1. I substitute the values and the C star will come out to be 1737 meters per second. Most of these rockets have a C star efficiency. We will know how to calculate it when we make when we study liquid propellant rockets, and the absolute value of C star we will assume to be 0.96 for the present. since I still do not know how to estimate this. I also say, well, the thrust coefficient in the nozzle, I know for the particular nozzle area ratio, I take the value as equal to, let us say 1.95, something which is realizable. Maybe for the particular area ratio my thrust coefficient is this. Well, the data is all available to me. Now I want to calculate the value of specific impulse. The value of specific impulse is equal to ISP is equal to, we say C star into CF, which is equal to, CF is 1.95, C star is efficiency is 0.96, the theoretical value is 1737, so much meters per second. I want a thrust which we said is something like 6.7 kilonewtons. Therefore, the value of thrust divided by the mass flow rate of the fuel and oxidizer total propellant is equal to ISP. From this I get the value of MP dot, right. MP dot is equal to thrust divided by specific impulse, and that comes out to be something like 2 kilograms per second. You can do this. And now what is the flow rate of oxidizer and flow rate of fuel? You know the mixture ratio is given as 1.5, m dot oxidizer divided by m dot fuel is equal to mixture ratio, which is 1.5. Therefore, I know m dot fuel divided by multiplied by 1 plus 1.5 is the total propellant mass, which is equal to 2, or rather m dot f mass flow rate of fuel is equal to 2 by 2.5. Okay. And once I know the mass flow rate of fuel, I know what is the value of mass flow rate of oxidizer, and this is all what is done. This might be around 0.8, and the total value of m dot oxidizer, which is equal to N2O4, is equal to 1.2 kg per second. This is how one solves it. It is extremely simple, right. Maybe one another problem which we could consider is something, let us say I have a solid propellant which consists of let us say ammonium perchlorate and oxidizer. I will just quickly go through it, we do not need to do it. I say I have a propellant which consists of, let us say, AP plus maybe HTPB. I say that the solid loading in this propellant is 75%. I give you the molecular mass of HTPB, I know the molecular mass of AP, namely NH4ClO4, and if this is given, I want you to find out whether with 75% solid loading, that means mass of AP in the total mass of propellant is 75%, this is what we called as solid loading. I want to find out whether this propellant is fuel rich or oxidizer rich. You can do the same thing. I write the equation HTPB, I know the molecular formula, the molecular mass is given to you, therefore I know the moles of this, I know the moles of this, I divide this divided by the total is 75%, I get the value of the number of moles of HTPB required for a single mole of AP, and then from this I can go ahead and find out whether it is oxidizer rich or fuel rich. You will find even with 75% solid loading, it will be terribly fuel rich. All propellants tend to be fuel rich. Why don't you all do this problem as a homework, because it is quite simple, and actually the liquid propellants what we use, the solid propellants what we use are quite simple. The solid propellants are made as a solid block, and in the next class we will see how to make a solid motor out of this block, as it were. Similarly, for the different liquid fuels, what are the cycles which we can use such that I can get them to expand and give me some value of jet velocity, and similarly for hybrids. This is all about propellants. Maybe in the next class we start with solid propellant rockets. Thank you then.